So I'm going to go back a little bit to the beginning since this was part of a recorded lecture. So just a quick reminder, flight controls ATA 27. You're familiar with should be familiar with all your primary flight controls, some of the secondary flight controls at this point. The new ones that you may not have seen before are things like slats, trimmable surfaces versus trim tabs, and then spoilers and speed brakes, and we'll talk about all those kind of in detail one at a time. The flight control actuation loop of control looks something like this, and I talked about this as well earlier. I've mentioned it before. It played a part in indication primarily, and that is from an indication standpoint, I talked about like hydraulics and indication is you turn on a hydraulic pump switch. It's not turning on the switch that gets rid of the low pressure message or the low pressure light. It's an actual pressure sensor downstream that sends a signal back confirming that the pump came on. Same thing with flight controls in the servo actuator. So on like the mechanical flight control, this loop of control is built into this mechanical linkage right here. Okay, that's what's happening between this arm with the centering mechanism and the actual control valve based on where the input is. And so that'll be loop of control there. When we get, in just a minute, we'll start talking about fly-by-wire flight controls, and that's done electronically. The other element of this is when you look on like an ICAS display, there are, on most aircraft, there is the ability to see flight control position on ICAS. So let me pull that up real quick. And when we look at it on, ICAS, I'm going to go out of full screen. It's preventing me from getting it open here. When we look on an ICAS display that looks like this, I realized I closed it by accident. So here's our sim, right? And let me zoom out. I had this all set and then I just closed it. Here's our displays, okay? Yeah, I had this all set. Oops, why did I close it? So here we have a situation where it is running. If I go over to here, and I'm not going to be able to see which one flight controls is without looking better. Electrical or status, top right. There we go. Oh, actually, we're on status. Sorry. So we're on the status page. You can see the status page down here. If I move the yoke around, you can see my elevator moving up and down there in the center. You can also see my ailerons, which are the two outermost here. Let me zoom in on those specifically and then drag this up. So here's my elevator. Here are my ailerons. And what else do you see moving there with my ailerons? The spoilers. So when we get to spoilers, we'll talk about spoilers assist and roll control as well. Okay. So you can see the spoilers on the, here if I bank left, my left aileron went up, my right aileron went down. Don't worry about the elevator right now. But along with the left aileron moving up, you can see the spoilers on the left side went up as well. Whereas the spoilers on the right are staying still, or staying flush. Rudder, oh boy, I'm on my laptop. I'm trying to remember where the rudder controls are. I might change too many. I can't remember which controls. Rudder, I have to use some keystrokes, so I'm going to just ignore that for right now. But you kind of get the idea. So that is not, I was using my mouse to move the yoke around. That was not, in the actual aircraft, it's not because I'm moving the yoke that causes those. In fact, if I shut hydraulics off, the flight controls won't move. None of those little indicators will move. It's the actual physical movement of the flight control has a sensor on it. And that sensor provides that feedback signal to the display in that case, which is just so the crew can verify movement of flight controls. It's also things like the autopilot. So the autopilot can see it moving. And then it also feeds into things like the flight data recorder. The black box, so to speak, the black box that records all the aircraft parameters. That box will be recording the actual physical movements of the yoke. It'll also be recording that movement of the flight control so they can be compared if there's an accident or something to tell, was it the crew doing the wrong motions with the yoke or the rudder pedals, or was it because the flight control itself failed to move? Okay. So part of that plane that the collision over the Potomac recently, as well as the aircraft that came in hard and rolled over just last week, I guarantee they're going to be looking at what kind of control movements were being made by the crew compared to what were the flight controls actually doing. Now, the one over the Potomac, I think they were trying, I've heard they were starting to take some evasive maneuvers to try to avoid hitting, the helicopter collision. But it was too late, likely. The one into land that rolled over in Canada, it'll be interesting to see what they find from analyzing the flight data recorder and looking at, among others, those parameters. Also look at things like engine RPMs and throttle position. They'll look at different systems information. That's all recorded on modern FDRs. So this loop of control, though, is what moves our flight controls. And even on flight controls that are not servo style, but where they go either full extended or full retracted, you're still going to have this feedback loop to verify that the motion is taking place like what's being commanded of the aircraft. I did a summary of the kind of 7 different styles, and we're looking at here, the key is we have how are they controlled and then what actually actuates the flight control. Okay, so how are they controlled? How does the signal get from the crew to the flight control itself, and then, or to the device that's going to move the control, and then what's actually moving the control? So you can have these 7 different types, and in the previous video, I talked about mechanical with hydraulic boost, and hydraulic with mechanical control. So mechanical control in that. Now we're going to start moving into the last 5 here. Sorry, 4, hydraulic with electric control, and then the ones below that. So we looked at purely mechanical. I looked at mechanical with hydraulic boost. And then I looked at what's probably the most common in transport aircraft, except for now moving into your newest ones. We've moved on from this. But what was most common for a long, long time was mechanical control with hydraulic function, hydraulic movement. And so here, this is where there no longer is, going from small aircraft to large, we've severed that connection, that physical connection between the person controlling the aircraft and the flight control itself. All it's doing, like on this actuator I have here, when I move, this was a rudder actuator, when I move the rudder pedals back and forth, my rudder pedals were connected right here to this little arm. And all that arm is doing is moving this valve right here, which is what causes the actuator to move back and forth. So you can see there is no longer a physical connection between our input and the flight control surface itself, because we've reached a point where the forces on the flight controls are so great that even if there was a physical connection, a person would not be able to actually move it. Right? We're getting beyond the physical limits of a human body can provide. And remember, it's not the guy who can squat 350 pounds we're talking about here. We're talking about the 5'4" woman that weighs 120 pounds, and maybe does like just the empty barbell, right? It has to be the full range of who could possibly operate the aircraft that has to be able to move it. Okay? So, and then we talked about the different types of control valves, which I did in hydraulics. But here's kind of that schematic of what this looks like. So here is a mechanical flight control system. So this is looking at the ailerons. So we have a pair of yokes up here. The yokes are tied together, and they're going to use these various cables to move. They call them quadrants, or they're basically bell cranks. So cables coming back from the flight deck into the wing box area between the landing gear. And then from here, cables going out to each set of what are called PCUs. Who knows what PCU is? Talked about in hydraulics. The PCUs are power control units. This is a PCU sitting in front of me right here. This is a rudder PCU. Okay, those cables are moving the little valves on there, and that's what's causing these PCUs to go up and down. You can see there's 2 on each side. Why are there 2 on each side? What does that provide? redundancy. They're going to operate on different hydraulic systems. So in this aircraft, for instance, it's a 3. This is an Embraer. This is either 170, 175, 190, 195. 3 hydraulic systems. So the left one is powered by hydraulic system 1 and 3. The right one, I believe, is powered by 2 and 3. But I could be mistaken exactly. But essentially, you have a division because you can actually roll the airplane with one aileron. You don't even need both ailerons to work. You won't have as much what's called control authority. It'll be lethargic. It won't roll as quickly, but you can still control the aircraft. Same thing with like rudders. Often they have 3 PCUs, or in the case of the 727, this was often had an upper and a lower rudder. So it had kind of 2 halves that would normally move together, but it could move one or the other. Elevators, you can just move the left or the right elevator. They're so close to center line, they don't really cause a rolling moment. They do a little bit, but you know, if you only can move one elevator, the left side or the right side, that's still going to pitch the airplane with minimal roll. Again, the ailerons are way out on the wingtips. That's why they're able to roll the airplane. So you can see the redundancy built in, and then we've got multiple runs of cables as well. These can actually, normally they're tied together. There's a disconnect unit here between the 2 yokes. Normally they're tied together, but if one side gets jammed, there's a handle you can pull in the flight deck that separates that disconnect, and then you can operate the system side or the other. So you can see there's not only redundancy in the hydraulics that operate these in the power control units, but there's redundancy in the physical input linkages as well. The cables, push-pull rods, tubes, bell cranks, all that stuff. So yeah, if the captain's side, if they get jammed, they'll separate them. They'll see who's can move. Say it's the captain's side is jammed, then the first officer will do the roll control, will control the aircraft at that point, or vice versa. So our next type now is electrically controlled hydraulic flight controls. And these are the other very, very common type you're going to see, particularly on anything modern, anything built after about the late 1990s and on, but not exclusively. When we get to the end, I'll talk about it's very common for aircraft to have some combination of mechanically controlled, hydraulically actuated, electrically controlled, hydraulically actuated. An aircraft doesn't have to be exclusively fly-by-wire. It doesn't have to be exclusively old school. And even sometimes you'll have a mix of like hydraulically boosted versus hydraulically operated in the small regional jet and large turboprop category. And so you'll see these combinations, or sometimes you'll even have one flight control that can be moved 2 different ways. I'll show you that as well. But this is where we get into what are called fly-by-wire. And that's a term that probably many of you have heard. And fly-by-wire, you know, don't confuse it with fly-by-cable, okay? Fly-by-cable is the cables that actually physically move the valve, push, pull. Well, pull, cables can only pull, but they're run in a pair, so they can pull, okay? Fly-by-wire is electrical wires. So we're sending electrical signals. We're creating an electrical signal at the input, and then we are feeding that into a valve, an electrically operated valve, to move the flight control. And typically it's going to run through a computer somewhere on the way to it that kind of interprets and operates everything. So there's no physical connection again. They can't be moved without hydraulic and or electrical systems. So we have to have a lot of redundancies and safeties built in to take that into account. And again, you're going to have the 2 valve types. So you're going to have a PCU, or control unit, with a servo valve. But now the valve is going to be, instead of a physical movement valve like the one here in front of me, it's going to have a electrical valve actuator. It'll move the spool valve or the rotary valve electronically with some kind of a motor or a torque motor, or even some of them use like magnetic fields with like a relay style system. There's different ways to move the valve to port hydraulic fluid to the different sides of the PCU in order to move the actuator portion of it. Now for input as well as feedback, we get into something called an RVDT or LVDT. I'll explain that in a minute, but those are the sensors that are going to provide the signal and also are going to provide the feedback signal. So they're going to sense how far did you turn the yoke for the ailerons. How far did you push the rudder pedals to move the rudder, and so on. Okay, how far did you move the steering tiller to turn the front wheels when you're on the ground? That can even be a fly-by-wire. It's not flying, but it's called a fly-by-wire system when you do that. You can also have your full travel actuators, the things that are either fully extended or fully retracted. Flaps, kind of, and they have stops, I guess, so not a great example, but things like ground spoilers. So slats will even have steps. They'll go through different steps. They're not always fully extended. So here is the control column, wheels, pedals. You're going to have aircraft wiring. It's going to go to typically some kind of control electronics. That's going to send the signal to the actuator. That actuator is going to have something to monitor its physical position, and it's going to send that signal back to the electronics. And then that oftentimes will have a signal going back to the ICAS, like I demonstrated in the previous one. Okay. So these RVDTs and LVDTs, everything above is the same. So are called linear variable differential transformers and rotary variable differential transformers. And I can spend a bunch of time explaining it, or we can watch the video. So I'm going to go ahead and do the video. What I do have the next several slides, I'm not going to go through them. I'll go through them a little bit. Kind of is some sketches I made of the operation of RVDTs, LVDTs, but they're going to cover a lot of this in the video here. Oops, go back. Okay, so I have my rudimentary drawings here, so hopefully you see a little bit. I can kind of demonstrate the difference. So here's that LVDT, and I'll go through these quickly because the video talks about it. So you can see I've moved my core just a little bit to the left. I've got a small positive signal. We'll call it positive because the arrow's pointing towards positive at the bottom there, right? And that's because you can see, so if I'm here, you can see I've got my positive, my arrow is pointing left to right, on both sides. But because here we've got the positive hooked up to the positive, down here they oppose each other where it comes together. So we get basically no voltage out the outputs down here at the bottom. But if I move it a little bit to the left, you can see the left side's gotten bigger, the right side's gotten a little bit smaller. And so what that means is our arrow pointing left to right is a little bit bigger than our arrow pointing right to left. So we end up with a positive and a negative here. But now what the video didn't show you is if you move the coil even further over. So now here I've moved it even further over, and you can see we got an even bigger, positive to the right on the left side and a much smaller one on the right. And now our positive negative difference has gotten even bigger. So that's where we get our how far did we move it? Not only our direction, but the amplitude or the degree of movement. Okay, and we take it back to we take it over to the right, and you can see it starts to reverse now. And so there they are kind of all together. So you can kind of see what's happening with my core moving side to side. My drawings aren't nearly as fancy as the YouTube video, but hey, they're a little simpler. So hopefully that helps to make it clear. Now, what wasn't talked about in the video was a rotary variable differential transformer, an RVDT. RVDTs work under the same concept. It's just instead of a core that moves linear left to right, we have a core that can rotate. So it's kind of this half moon shape is the most common. So here's our input coil at the top. Here's our two coils at the bottom, kind of arranged, in a circle around the core. And right here is like our null point. You can see the core is kind of equally distributed between the left and the right coil. So we get equal arrows and a zero. But what we can do now is rotate our core. So if we rotate the core, you can see there's a stronger coupling into the left coil, a weaker coupling now in the right. And so now we get that, in this case, positive arrow to the right again. If we turn it further, we get a bigger output EMF, a bigger voltage across the outputs. And if we turn it to the right now, you can see it reverses direction. Okay? So again, if I put them all side by side, we can, and here I wrote counterclockwise, I guess. So if we turn it, null in the center, if we turn it a little bit counterclockwise, we get a positive one way. Far counterclockwise, we get a positive that same direction, but in a larger magnitude. And if we turn it counterclockwise from its null position, now that reverses. And again, we can vary it depending on how much we turn it. We can create a stronger or weaker output voltage, EMF. And that directly correlates to how far we've either moved the input or how far the flight control or whatever else these are controlling has moved after it's made its movement. So that can provide our input as well as our feedback. And what's the advantage of these? Why do we use these? You put them right in the yoke. What about like a variable resistor? It uses physical contact. That's one reason. What's the problem with physical contact? It can wear out. That's the biggest reason. Do you see any contact taking place in either of these? That core, all it has to do is be able to slide back and forth or rotate, right? So there's no physical contacts to wear out in these. It's not saying they don't ever go bad. Usually if they go bad, it's because the little input shaft breaks somehow, or one of the coils shorts out. You know, they burn out, they get a voltage spike, you know, or something like that that causes a coil to burn out. But they're much more reliable than something like a variable resistor. They also have the ability to reverse. Variable resistors can't reverse, right? They can go lower and higher. You could always put it in the middle, right? If you have, you know, 50 ohms of resistance, that's 0, and 0 ohms of resistance, that's fully right, and 100 ohms of resistance, that's fully left, right? But if that fails, say it fails open, what do you get? Usually either 0 or 100, right? So it's going to think it goes one way or the other. If one of these fails, they don't get any kind of a signal. They basically lose output, or they get weird signals. And so typically these are done, not only are they more reliable, but typically we have at least 2 of them providing input signal and 2 of them providing position monitoring on the output side when they're used in something critical like a fly-by-wire system, a flight control system, or even our nose wheel steering on the aircraft that had these. There were 2 of them in the tiller, and there were 2 of them down on the actual, the hydraulic actuators that turn the nose wheels left and right. Yeah. Yeah. It could get stuck. Usually whatever's turning these is pretty strong, right? They're connected to a flight control that's going to be hydraulically driven. There's a lot of even if it's in like the steering tiller, you got a lot of mechanical advantage on it. And that's why we use 2 in case one of them's giving erroneous signals, or if they don't match, like our nose wheel steering, if it wouldn't match, it would just shut off. You get a ICAS message, nose wheel steering and up. And then at that point, you can just steer using like differential braking, left brakes, or by differential thrust, throttle up the right engine or throttle up the left engine. So we could still steer. In fact, when I was teaching people to run taxi, they would be in the left seat, I would be in the right seat. The circuit breaker for the nose wheel steering system was right down by my knee. We'd be going along nice and happy, and I'd just kind of reach down and pop. They wouldn't even know it. But it allowed me to run a scenario as part of training where, okay, now get us back to the hangar without having nose wheel steering. You know, basically castering, like if you've ever flown in the Cirrus, they have a castering nose wheel. You use it with, in that case, with the rudder, but by routing air from the propeller across the rudder to swing the tail around. In the case of these, you could use, main thing we used was differential braking, but you could also use differential thrust to some extent. Wing-mounted engines definitely have much more differential thrust. It just takes some time to react. So if they do go bad, there are ways to deal with it. On flight controls, we'll get to what are called flight control laws in a second, and that is if you lose certain amounts of signal or other things like that, there's reversionary modes to make sure that your flight controls still work properly. So here is that loop of control. Now with a fly-by-wire system rather than the mechanical system. Okay. And so here we have our input yoke, and you can see now I'm using the positive and negative, right? That can be different magnitudes that we're getting from the RVDT or LVDT. You'll often hear them just referred to as a VDT, Variable Differential Transformer, right? Doesn't really matter, RV, R or L is purely just packaging. Do you want it to spin? Do you want it to slide? Okay. So, you know, here, if I have my yoke, I'm showing a elevator in this case. If I move it one way, I control how far I go nose down. The other way is how far I go nose up. That's going to send a signal to the computer. which is going to send a signal out to the actuator. And then there's going to be a VDT monitoring that. That's going to send feedback to the computer. And what's going to happen is, what you'll notice here is, like in this case, the most common design, if I go nose up, you can see nose up is positive at the input. And if we look at our output, you can see nose up here, which is the trailing edge up, is negative. And so what the computer essentially, simplest form, is looking for is, if I put a certain amount of positive at the input side, it's looking for a certain amount of balancing negative at the output side, or at the return side. And it's just going to balance them back out. It's going to move the flight control actuator until they balance. So you can see they look similar if I put them side by side right here. Right? So if I move this a little bit, I'm going to get a little positive, little nose up. It's going to move this thing, this flight control, up till it's got a little bit of negative. And they balance each other out. They equal 0 again. So the signal from the VDT sum to 0. If I move it all the way to the big positive, it's going to move this actuator until the trailing edge hits all the way to the negative, big negative nose up. They're going to balance each other out. It's going to stay 0 until I bring this back to the 0 again. Then it'll have a negative signal coming in, and so it'll tell the actuator to go more positive until it gets a 0 to match the 0 over here. Right? Pretty, seems intuitive, right? It's basically an algebraic equation. Make the left side equal the right side. The computer is the equal sign in the middle. And so it balances, yep. And what we can do, though, is we can put more than one input into here as well. So down the road, we'll look at like trim. Well, one way to trim is just to put a little bit of a, we can have another signal coming into the computer saying, I need a little more nose up trim. So it puts a little more positive coming in this side. And so then the computer can move it to, so there's ways to trim using this. You can use the autopilot as an input, right? So the yoke, you keep your yoke in the middle, but then the autopilot gives positive and negative signals. And the same actuator and same feedback does its thing. Right? So it's very simple, very elegant to allow our system to do this electronically. And the other part, though, is our computer can also kind of interpret what's going on with the input signals, and it can make some decisions too, or there can be logic in there where it's not always a one-for-one. Okay? Airbus was big on that. They did what they called their control laws, and those are, if you're in takeoff and you pull back on the stick, all you got to do is pull all the way back. It's going to take the plane to best climb. It's not going to stall. It's going to move the flight control right up till it gets to the stall point, but it's not going to actually keep nosing up until the plane stalls. Compared to a Boeing, if you pull all the way back, it's going to just keep nosing up. They didn't use that at first. They do now. They have more control laws in place now. Okay. It could, but it can also, if something goes wrong, like the air show where the A320 went into the trees, part of that was attributed to an issue with the control laws. So it was actually an understanding of how the control laws work and things like that. But anyways, so these are going to have, that's what I was talking about, the multiple control laws. So that means that these systems can actually be programmed to adapt to phases of flight. They don't always have to behave the same. If you have mechanical controls, they're pretty much going to behave the same no matter what. But if we're running through a computer where we can provide some kind of interpretation of the input and an adjustment to the output, now we can adjust phases of flight. So the example I was talking about, system conditions, part of it. So example, so phase of flight, then system conditions. The other part is system condition. Remember I said if we lose hydraulic systems, say we lose 2 hydraulic systems and 1 aileron, right, is only being powered, we only have 1 aileron, that's going to cut our roll authority in half. The computer may actually double the amount of normal deflection on that side to try to make up for that at low deflection angles. Right, so we can go into, that's what we're talking about, system condition. It's going to look at how many hydraulic systems are available. How many VDT signals am I getting? Do I have some reason that I can't track the input or the position of the flight control as accurately? Or am I as sure about what that position actually is? So normal laws, when everything's working right and we're on the ground or flight or the flare phases, so ground and low speed, we get full pitch and roll authority. But the flight, once we're up in flight, the pitch becomes G limited. G limited means I cannot, if I go into a dive on an Airbus and I pull all the way back to pull out of the dive, it's not going to pull out of the dive so strong or so hard that the wings are going to snap off or the tail is going to snap off. It's going to try to keep the airplane within its normal G envelope. For roll, they have direct control to 33 degrees, but then once you get above 33 and get to 67, it actually starts to taper off the amount of roll you have, so you don't accidentally over-roll the aircraft. And it will not allow it to roll past 67 degrees. So if you hold that all the way to one side, that plane's going to roll up to 67 degrees. You cannot barrel roll an Airbus if it is in normal control law mode. It will roll to 67 degrees and it'll stay there while it does a big circle. When you're in flare, you give pitch full authority. That's below 100 feet above ground level. When you want to flare the aircraft, you want to be able to flare the aircraft. What happens when you don't flare the aircraft? We saw it last week. There's a potential that they didn't have time to flare, that didn't flare for some reason. That's why that landing gear, that's part of what probably contributed to that landing gear collapse. Okay, they came in too tight. They couldn't flare, which is where you pull up at the end to slow your descent rate right before you touch down. So when you flare, you want to be able to flare. You actually are kind of stalling the airplane into the ground a little bit. Okay? It protects against high angle of attacks, load factors, high pitch attitudes, overspeeds, excessive bank angles. Those are all feeding in, and the computer's like, no, I'm not going to let you do that. Nope, you're doing a bad thing. Okay? So that's the normal laws. We'll talk about some of the other laws next time.